Welcome, everyone. Welcome to today's webinar, Replicating Your 5G Open WAN Network in the Lab to Save Time, Test More, Get to Market Faster. Sponsored and represented by brought to you by Accenture. In today's session, we will, however, take a closer look at the testing domain and system architectures themselves. We will discuss why the tools and processes formerly done in the 4G world cannot be done in 5G Open WAN world without introducing risk. Mirror Lab helps reduce those risks by helping more closely represent the real end-to-end network as much as possible. Our speaker, David, will also cover several Mirror Lab use cases, which incidentally is my favorite part about today's session. Before we begin, just a little context about Accenture. So since 2011, Accenture has been working closely with carriers building test and measurement solutions. But by 2013, Accenture has shifted into a product innovation technology company that develops and supplies hardware and software products. We have four main divisions. First is Radiocom, a low-PIM passive networks components line for both in-building and outdoor solutions. We have Lambda, a software platform for RF lab management and automation, as well as lab resources management. Omera, our software orchestration platform to help automate and help carriers with deploying their next-gen networks. And Symmetrix, our independent subsidiary company that offers RF filters with a filter design and manufacturing aided tools to help manufacture filters on the production line. So a bit about the speaker today, David Woodcock. David is a Waterloo Systems Engineering alumni with several decades of experience in the wireless industry and has had several technical and business roles throughout that period. At Motorola, he designed many of the first public safety trunking radio systems here in Ontario and Canada. And later on, Motorola was responsible for launching the iconic Motorola Razr. While at HTC, his team was responsible for launching the very first 3 Android smartphones in Canada. As of late, David has taken more on the commercial side, has been doing more sales and business development roles from a global perspective, and also has responsibilities as a product strategy role here at Accenture. So with that, I'll pass off to David.
Thanks very much, David. You're right. It's been a while since I've carried the pocket protector in a technical role, but I still like to keep those skills sharp. So it helps in cases like this. So thank you. Welcome, everybody. Thanks for taking some time out of your day to join us. As David said, I've been with Accenture for a couple of years now, and I have some sales responsibilities, but my involvement in product strategy is the reason that I'm speaking here with you today. Here's what we're going to cover in the next 30 to 40 minutes or so. First, we're going to talk about some of the challenges created by 5G and the general trend of telco network virtualization and migrating networks to the cloud, particularly how these things relate to testing. Next, we'll compare traditional testing methodologies of the telco and cloud worlds. And finally, we'll explore the concept of the Mirror Lab as a testing strategy, a way to replicate the production network in the lab to save time, test more, and get to market faster, and reduce risk at the same time. I will warn you that there is some audience participation coming, so get ready for that, be on your toes. And if you have any questions, please submit them using the Q&A function, and we'll do our best to get to them at the end of the webinar. So let's get started. There's no question that 5G has arrived for real, and that means emerging network architectures, more frequency bands with different propagation characteristics, and new services. We can't forget that 4G and even 3G are still around and will be for a while. And that means multiple technologies in use at the same time. Operators are embracing the telco cloud and network virtualization. The concept of virtualization separates the software functionality from requiring dedicated purpose-built hardware, enabling it to run in the cloud. These architectural changes offer a lot of flexibility and agility for operators in terms of service deployment, scaling, and performance, but it's new territory for them, and it's a pretty fundamental change for the industry. Another trend is Open RAN, which in plain language is the ability to mix and match several vendors' hardware and software together in ways that wasn't possible before. We expect this to be financially beneficial for the operator, but it introduces significantly more complexity into the network and the business of running the network. These trends mean that the typical mobile network is more complicated now than it has ever been. And this has very real implications for testing strategies. We're going to talk about how operators can adapt their testing processes to address these new challenges. But first, let's spend a couple minutes looking at how things are done today. This is a dramatic oversimplification, but the left side of this slide shows traditional network architectures in the world before 5G. Networks were purpose-built, highly vertically integrated, and generally supplied by a single vendor. Sure, operators had multiple vendors within the same networks, but the interface points were minimal and pretty tightly controlled. Notably, there's only a handful of players in the game back then, and you can see the usual suspects here. The advent of 5G, and especially Open RAN, introduced a lot of new suppliers into the industry, as you can see here on the right. The incumbents are there, but there are new RAN vendors as well, like Mavenir and Bicells. Virtualization has brought several other companies into the mix, like Red Hat, Wind River, VMware, and opened the market to commercial off-the-shelf hardware suppliers like HP and Dell. Not to be left out of anything, the hyperscaler cloud platforms like Azure and AWS and Google Cloud are participating too, with many operators already working with them. A recent survey done by Jabil of 193 companies, 55% of them are considering Open RAN. Another 22 already have plans in place, and the majority of those will include the major public cloud vendors. So all this means that the combinations to test are increasing a lot. So let's take a closer look at why. Here we see the typical 4G network architecture with the enhanced packet core, the BBU, and RU. It's pretty straightforward, with the one really only real deployment question is where to locate the BBU equipment. Is it centralized with the core, or is it distributed with the RF equipment? The equipment and the suppliers are the same. In the world of 5G, the BBU is disaggregated, and its functions can exist in a variety of places on different hardware. These variations are called functional splits, and there are 8 major ones, although some are a lot more common than others. I'm not going to go into why some of them are used over others, except to say that the operator decides which ones to use based on a whole bunch of different factors and requirements and constraints, such as latency, QoS, traffic loads, and the available bandwidth for things like backhaul, mid-haul, front haul, and the cost and scale of the bits in the network. It's common to combine multiple splits into the same network to address different network site density and service offering requirements. This diagram shows an example of 3 different functional splits, all controlled by the same 5G core. As you can see, the 5G network architecture has many more variations than prior generations. And this doesn't even begin to show the additional complications of virtualization. In simple terms, running various network functions in software containers on a standard server somewhere. The server can be in a data center that could be private, it could be public, or even in a hybrid cloud. So it's not a stretch to say that there are many more variables than there were in 4G and before, and there's a lot more permutations and combinations in 5G. So let's pause for our first audience participation poll that I promised. So David, if you can throw this one up, and we'll take a couple minutes for people to respond, and then maybe you can give us the number 1.
You should see it on your screen now. I'll just give it a few minutes, or a few 10 or 20 seconds. Getting some results now, Dave. Just give me maybe 5 or 10 more seconds here.
Sure. Curious what people think.
Okay, last couple seconds here. We'll end the poll here. We have over 50% of the responses on evaluating the performance of virtualized parts, another 33% implementing and managing different brand splits, and then we have one answer on the integrating COTS hardware in the net.
Very good. So people are worried about a lot of different things when it comes to 5G. So we know that wireless networks are getting more complicated, and all parts of the network have to work together to deliver services and the customer experience. In the past, the operator could rely a lot on their infrastructure vendor partner to handle a lot of this with purpose-built, highly integrated equipment. A lot of the testing was done beforehand. The operator focused their testing efforts on validating their specific configuration choices with the subscriber devices on their network to make sure that their services were delivered properly. As a result, their testing methodologies focused on this part of the network, the lower parts of the RAN. In our experience, there are a few different testing methodologies used by operators to do this. Some operators rely on their network and device vendor partners to do a lot of the testing, and they pick a few key performance indicators to monitor. They might test parts of the network in isolation or perform user testing from a customer perspective. This is the simplest approach and is typically used by smaller operators. Many operators rely heavily on emulation, which is also part of a reasonable testing strategy. In essence, this is simply a UE talking to something pretending to be a network, or a network talking to something pretending to be a UE or many UEs. But emulation, even when done at scale, doesn't really reflect the actual real world environment because there are too many things missing from the model. The emulation equipment makes too many assumptions about network configuration that don't represent that operator's specific implementation. Still, other operators create a testing environment that replicates the real world in the lab to really evaluate what the end user will experience. This approach uses real world equipment to the largest extent possible. Real BBU and RRUs, actual user equipment, and sometimes even the specific RF designs, frequency assignments, carrier aggregation, MIMO. This requires the most gear and human resources, but it delivers the most representative testing. However, each of these still really only consider the lower parts of the RAN, and a lot of them don't include everything that is different about that network. Now that we've looked at the tools, let's talk for a minute about the process. The current practice for RAN testing looks something like this. Each test is generally independent and done to validate a defined set of proposed changes to an existing configuration. This might be something exciting like a new service, maybe something a little less exciting like a new version of base station firmware, or maybe even to help troubleshoot an issue in the field. Tests are typically set up manually, which can take a long time, maybe even hours or days, depending on the complexity. In fact, we see that the setup and teardown times are often far longer than the actual testing itself. At the end of each cycle, network engineering takes the results and deploys that change into the production network. Monitoring of the network happens in parallel through the usual tools like OSS and BSS. And they measure key performance indicators, which are monitored to determine what changes need to be made in the future, which in turn results in more tests to do. If you're familiar with software development, this approach is very similar to the waterfall method, where each release is developed, tested, and deployed sequentially. And the time between iterations is relatively long. This is perfectly fine in the world of 3G and 4G, where things don't change very much or very often. It's not fine in the world of the cloud and virtualization, where things are constantly changing. Now that there are more possible architecture configurations, including virtualization and public cloud, more vendors and new services, the existing approach leaves a lot to be desired. The operator has a lot more things to test and less time to test them. In prior generations, the network changed at a much slower pace. In 5G networks, especially virtualized ones, the network will change constantly, including parts that never changed before. Features like network slicing and services that demand very low latency or extreme bandwidth require the dynamic reallocation of resources and the migration of functions from one layer of the network to another. There are a number of variables for each part of the network that will affect performance. And when these can change dynamically, the pressure on the testing environment grows considerably. Each of these changes need to be validated before deployment. But here's the thing, the operator won't be able to wait weeks or even days for the testing to be completed. Testing needs to be done in almost real time. There's also new things to think about in the physical layer too. 5G brings new RU designs, new frequency bands with different propagation characteristics, new RF site designs with higher orders of MIMO and even massive MIMO. There's coexistence with 3G and 4G. And of course, there's new types of user equipment as well with the growth of IoT. This is a challenge even for mobile operators who have well-established test methods. It requires investments in new testing tools and skill sets that weren't necessary for previous generations of network architectures. It requires a new approach to testing itself. Fortunately, we can look to the cloud computing world for some new tools and processes that can handle this constant change. Cloud-native companies rely on a practice known as DevOps, which blurs the lines between the roles of development and operations functions to cope with rapid change and still produce quality output. The idea is that the more closely these two groups are integrated, the more communications will be streamlined and things can happen more quickly with fewer mistakes. At Accenture, we think there are lessons to be learned from this. To really take advantage of the potential of 5G, mobile operators will have to change how they test and deploy their networks and start approaching the problem the same way that the cloud companies do. It's not just about RF testing anymore. And it also isn't just about Kubernetes and servers and cloud native. It's about having all these things working together to deliver services. The RF and IT worlds coming together to solve the challenge. One of the ways to do this is a process within DevOps known as continuous integration, continuous deployment, commonly known as CI/CD. CI refers to the automating the testing and creation processes, while CD refers to the packaging and delivery of the product. Of course, in the IT world, the product is software and therefore entirely virtual. But in the world of wireless networks, there are very real bits of infrastructure. Can this CI/CD stuff really work for us? We think the answer is yes with the right tools. Before we go any further, one more audience poll. I'd like to get an idea of how familiar everyone is with the concepts of DevOps and CI/CD. So let's take a moment to see where we fall here. David, maybe we'll give it another minute or so, and then we'll see where we land.
Just getting some responses now here. We'll give them another 5 to 10 seconds here.
You get your votes in.
Okay, so 55% familiar with the concept but never used it, 36% some experience, and 9% never heard of it. Just a reminder, folks, also that if you have questions, you can use the Q&A button icon at the bottom of your screen. We will collect those at the end, and hopefully we can answer them.
So no DevOps masters. We had a DevOps master the last time we put this question up. So I guess the next couple of slides may be worth it for the audience here. We'll take a closer look at CI/CD. In the software world, CI/CD is a closed loop cycle that compiles incremental changes and then packages them into releases. Automated tests verify those releases, and automated deployment services deliver them to the production environment. The continuous development tasks are shown here in the light blue, continuous testing in the darker blue, and continuous integration, deployment, and monitoring are shown in the yellow. The aim is to discover defects quickly, increase productivity, and provide faster release cycles. Basically, there are more releases, each with fewer smaller changes. This contrasts with the traditional methods that we just looked at, where a collection of updates are integrated into one large batch before being tested and deployed together. CI/CD helps deliver several benefits. First, organizations that use it have clearly seen significant quality improvements. This results from a few different things, but mainly because the testing regimen is much stronger and catches defects more quickly. The short cycle times between releases means that any escaping defects are fixed more rapidly as well. The continuous nature of the process means that the deployment cycle time is much faster as well. Cloud native companies can release new versions daily or even more frequently. You might think that the continuous nature of the process would lead to chaos, but actually the opposite is true. The regular test release cycle creates a stable environment because it is so regular. The organization doesn't veer from guardrail to guardrail anymore as people panic when release dates approach. Every day is release day. And the automation of the more mundane tasks leaves time for more value-added work. All the smart people you have can focus their time on innovation instead of manually running test scripts and reading log files. So it's clear that this is a useful approach for launching products in the software world. So now let's see how we can apply it to the concept of testing of things that are not virtual, like parts of 5G RAN. The 5G core and upper layers of the RAN can be virtualized. And by that, I mean turned into software running on a server somewhere. So CI/CD applies well here. But what about the physical things like RRUs and the mobile device at the other end? The mobile network also includes the physical medium of RF, which can be used in different ways within RF engineering techniques, such as MIMO and carrier aggregation to increase coverage and bandwidth. These are essential to delivering the service to the paying customer. How do we bring these parts of the system into this cycle of rapid testing? This adaptation of the CI/CD diagram in the previous slide shows how we can start to think about that. There are parallel activities in the physical testing world that match those in the virtual software world. Here, the light blue shows the physical equivalent of the software development activities, and the dark blue shows the physical testing activities. So the CI/CD model fits, but we're not quite there yet. To be truly CI/CD, everything here must be automated. Again, this is relatively straightforward when dealing with the virtual or cloud-based portions of the network, but the physical elements shown here in the dark blue are a different matter. This part of the CI/CD loop needs new automation tools that can tie all the physical elements in the lab together to automate the test setup, execution, and analysis of the results. That tool is the Mirror Lab. It's just what it sounds like, a reflection of the production network in the lab environment. The same equipment configured the same way. This means that any testing done in the lab is directly applicable to the production environment. And to maximize effectiveness and embrace the CI/CD concept, everything in this lab environment must be automated and managed. Now, I hear some of you thinking, this sounds a lot like testing automation. I already spent a lot of money on that. What do I need this for? It's a fair question, but there's a key difference that I want to highlight. Testing automation is what it says. The tests themselves are automated. However, to embrace the concept of CI/CD and recognize the need for rapid and frequent testing cycles in 5G, we also need to automate the activities surrounding the testing. We need lab orchestration and management to automate these activities. Planning the tests, deciding what tests are required, setting up the tests, configuring test equipment, and assigning resources to the tests, both equipment and people. Executing the tests, of course, and then collecting, organizing, and interpreting the test results. Those are all highly manual and time-consuming. A properly equipped Mirror Lab addresses these activities with an orchestration layer to manage and control the testing setup, execution, and result evaluation processes, and the associated lab resources, both equipment and people. Let's take a look at the essential elements of a Mirror Lab. We'll examine each of these in a bit more detail in a moment, but here's a quick summary. End-to-end network aspect is needed to accurately mirror the production environment. Of course, it's a subset of what's out in the field, but it should be a representative one. Such as every combination of RRU vendor, network architecture, configuration, and frequency plan. The orchestration layer is a key feature of the Mirror Lab. This layer controls and coordinates all the equipment and resources in the lab, network equipment, RF switch matrices, devices under test, and even people. The orchestration layer ensures all these work together to seamlessly test. Testing automation, the ability to run tests and collect logs at scale with limited human involvement is a key element of CI/CD. And log collection and analysis, gathering, organizing, and interpreting the results of the testing from all elements of the system, UE and network, in a way that can be quickly evaluated by the testers, who can spend more time on higher value activities. In summary, the Mirror Lab blends the lab and production environments together, accurately replicating the real world in the lab. It enables more sophisticated testing scenarios like roaming and handover, but with the actual radio access technologies, frequency bands, vendor equipment, and RF site designs that exist in the field, including specific MIMO and carrier aggregation configurations. Voice, data, video calls, messaging, etc., can all be validated in near real-world conditions for any network configuration. So the results are a lot more representative of what will really happen in the field. In fact, some of these kinds of tests are simply too hard to do any other way. A Mirror Lab allows for the optimal use of test resources, whether those are physical equipment like RRUs, software containers running various network functions, or people. Since everything is coordinated and automated, it's shared efficiently, and there's no wasted time caused by resource blocking or people using test equipment that wasn't assigned to them. Let's be honest, how many times has a test been accidentally ruined by someone borrowing a piece of test gear that was already in use by somebody else? Doesn't happen anymore. This reduces the time to market because the overall testing cycle is quicker. Specifically, the test planning, configuration, setup, and teardown times are reduced from days to hours and hours to minutes. The tests themselves can be run faster, more consistently, and more often by software than any human could ever do them. The tests are perfectly repeatable thousands of times in a way that isn't possible manually. So the confidence in the test result is much higher. And the collection, organization, and interpretation of the results is also automated. The orchestration of these other activities takes the more time-consuming manual steps out of the entire testing process. And yeah, it's time for another audience poll. So we've talked about some of the pain points that RF lab managers experience on a day-to-day basis. Let's see how common some of these are. So David, if you can throw that up. And
Here we go.
so this is a choose all that apply.
Oh, now we're starting to get some.
We should try to guess ahead of time where we're going to land.
Pretty
That's my favorite answers.
Pretty evenly distributed right now. Give it another 5 to 10 seconds here. Okay. Oh, a few more here.
Okay.
Yeah, it's pretty.
Give us our top two.
Yeah, I would say configuring test equipment. Configuring test equipment and interference from identified uncontrolled RF sources, and running complex tests manually. Those are the three right there.
All right. So those are problems that we can definitely solve with this kind of approach. All right. So far we've talked about what a Mirror Lab does. Now let's talk about what one actually looks like. First, there's the end-to-end network aspect. The concept here is to use your network to test your network. Use actual RAN and actual subscriber equipment because this is the best way to understand what's really going to happen out in the field. By all means, use some emulation as well. There's always a place for that, but focus on end-to-end testing of the real thing as much as possible. In this diagram, the lab on the right contains everything that exists in the real world on the left. The actual RAN equipment, including RRUs on every frequency, whatever CUDU splits are used, and any degree of virtualization is set up exactly the same. The end user devices are real and contained in Faraday cages, which can be anything from a small desktop shielded box to a full-size walk-in anechoic chamber, depending on what you're testing. The RF channel is recreated using a software-controlled RF switch matrix. This device takes a series of independent RF inputs from the RRUs and can mix them in any combination and send them to any combination of outputs. In this way, a fixed set of RF sources can be shared by multiple testers simultaneously. By combining the signals together, it can replicate various MIMO and carrier aggregation configurations. By varying the attenuation for each signal path, it also replicates conditions such as handovers and roaming. The result is that the UE sees what it would see in the real world. And the number of simultaneous tests is limited only by the number of RF chambers, since all the other resources are shared. The next piece of the Mirror Lab is the orchestration layer. This is the feature that connects all the assets together, configures them for the specific testing purposes, and organizes and manages their use. Here we see that the lab manager is able to perform test setup activities from anywhere, as well as assigning lab resources to specific testers who can also be anywhere there's an internet connection. Tester 1 here, shown in yellow, is assigned some RF resources, the 4 RAUs in the yellow circle and 1 RF shield box with a UE for testing. Tester 2, shown in green, is assigned a different RF shield box and 4 RAUs of their own, including 2 that are also being used by Tester 1. We can continue to add testers in parallel up to the number of available RF shield boxes. Because all the RF signals are routed through the any-to-any RF switch matrix, they can be shared by multiple testers simultaneously without any blocking. This makes more efficient use of scarce lab resources and prevents disruption or delay of testing results that happen when people grab whatever piece of test gear they see first. Each tester has everything they need to perform their assigned tasks right at their fingertips or mouse pointer. To facilitate test automation, each resource in the system is controlled by the orchestration layer and configured according to the scenario being tested. Here we're showing the 5G core, higher levels of the RAN, CUDU splits, the RUs, and the devices under test, but any equipment with an API can be included. The RAN is configured just like the production network, and the DUT are set up to make different call types, voice, video, data, messaging, etc., as required by the test plan. If there are already testing automation solutions present, the orchestration system integrates them into the overall process as well. Next, the various call types are automatically started on the devices under test, and the RAN equipment broadcasts signals into the RF switch matrix. The orchestration layer controls the RF switch matrix to execute the RF portion of the tests without human involvement. Various call types are made under different RF scenarios like roaming, handover, different orders of MIMO, and carrier aggregation by controlling that RF switch matrix. Changing which signals are combined together duplicates carrier aggregation and MIMO, and changing the attenuation of the signal paths mimics handover between sites. Because the switch matrix is under software control, it can manipulate many RF signal paths independently all at the same time. Trying to perform a 4x4 MIMO test with 3 carrier aggregation using manually controlled rotary attenuators would be next to impossible. It's almost certainly not possible to do it exactly the same way twice. This approach enables a more sophisticated tests that can be executed quickly, and they can be repeated perfectly as many times as necessary. Each test is run just like the previous ones. Finally, the orchestration layer collects logs from each element of the system for review. It also organizes and interprets them against predetermined pass-fail criteria and presents the results for review by the testers. All of these capabilities of the Mirror Lab frees up the smart and expensive testing resources from the mundane tasks of routing RF patch cables and reading through log files, and allows them to focus on higher level, more valuable work. Okay, one more audience poll, a pop quiz this time to see how much you were paying attention. Which one of these statements is false? Let's see who's sleeping and who's been paying attention.
Give me a few seconds here, David.
If you don't get it right, your homework is to go back and rewatch the webinar.
All right, I'll give it a couple more seconds here. All right, 2/3 of the responses was one of the benefits of the Mirror Lab is that it separates RAN and device testing. And yeah, we got a couple other answers to the telco cloud migration, workforce, et cetera, and they all said Another was orchestration and management layer coordinates and controls our resources in the mirror lab. But
So-
over 2/3 was one of the.
Okay, so the correct answer was 4, or one of the benefits of a mirror lab is that it separates randomized testing. That is false. One of the benefits is that it integrates them. So good for those who are following along there. Okay. So now we're going to look at 3 examples of specific mirror lab implementations that replicate particular network environments. The first here is an operator who wants to be able to test their 2-vendor 4G implementation in the lab, where each vendor has 2 different configurations. It looks like vendor A is used in high density areas with 2 carrier aggregation, with both CRAN and DRAN configurations. Vendor B is used for lower density sites, perhaps rural areas, and only single carrier deployments, but they also have both CRAN and DRAN configurations. The next example is a 5G operator that's replicating their dual split implementation in the lab. It looks like we have a 5G site on the left there in a split 2 configuration, which is suitable for delivering service in places where the mid-haul performance isn't great, like maybe a rural area. It could also be for delivering higher capacity services where you need some baseband processing near the edge, such as high traffic areas or in buildings. The right-hand side is a 7-2 split, maybe using mid-band spectrum because I see 4x4 MIMO here. These are probably for wider area coverage needs. And the third example is an operator that has both 4G and 5G networks running simultaneously and wants to replicate interoperability in the lab. The 4G network has a combination of 4x4 MIMO sites and some 2x2 MIMO sites, presumably to represent a mix of high and low density deployments. The 5G network is split 7-2, which is reasonably cost-effective architecture, especially with the virtualization of the CU and DU, as we see here. So it's possibly a 5G overlay to a 4G network. These mirror lab implementations are set up to allow the testing of all types of customer services on each of their network configurations, including the actual RF designs that exist in the field. They enable roaming and handover testing between and among any combination of the operator site configurations. The number of RF shield boxes determines the number of simultaneous tests, and each of them can share all the same network resources. Obviously, these aren't the only options. The combinations are almost endless, but the idea here is to implement a representative sample of the production environment in the mirror lab so that all real-world scenarios can be tested and performance validated. To expand on the examples we just looked at, we could imagine an even more sophisticated mirror lab that combines all these network architectures together. By combining the outputs of the various switch matrices together into the same set of RF chambers like we see at the bottom here, we can replicate a single network with all these different configurations and implementations. The user equipment in these shield boxes can make calls on and be handed off between any of these networks. One of my favorite pictures. It's one of the side benefits of an implementation like this. The lab gets a lot more organized. Typically, RF test engineers need to continually trace RF signal paths through patch panels like the one on the left here, and reroute them through a variety of splitters to feed different chambers. The result is a constantly changing test environment. So test reproducibility is difficult, if not impossible. And honestly, it's just messy. With an automated mirror lab, there's no need to keep tracing and rerouting cables. You cable everything once, lock the cabinet doors, and let the orchestration system handle the rest. So hopefully I've gotten you thinking about how a mirror lab implementation can help save you time, test more, and get to market faster. If you're interested in learning more about how to build one, we'd be happy to speak with you about our Lambda solution. It's used by multiple operators and equipment vendors to run their RF labs and testing operations. Lambda is an orchestration platform that applies the concepts of DevOps and CI/CD to the testing of the 5G RAN. It enables end-to-end testing of the entire system using a combination of RAN, devices under test, and emulation. It allows lab resources to be shared among multiple users simultaneously, and those users can even be in different locations. And it provides a management platform to plan and track testing activities. Using Lambda, tests setup takes minutes instead of hours or even days, and testing can be done quickly and repeated hundreds or even thousands of times. Since human involvement is limited, the tests are perfectly repeatable, which means higher confidence in the results. And once testing is complete, Lambda captures and organizes the system logs, eliminating a lot of tedious manual work, reducing the chance for human error, and it lets your resources focus on more valuable work. In a sentence, Lambda enables faster and more sophisticated testing and allows you to get new products and services to market faster with less risk. So with that, I think it's time to check to see what questions we have. I think, David, you've been collecting those.
Yeah, there's a couple here. Let me just start with the first one. Again, for anyone that wants further questions, please use the Q&A button icon at the bottom of the screen there and really type them in and we'll get to them in the session live if we can. So first, David, is if you are using actual network equipment, how does emulation fit into a mirror lab?
It's a good question. So emulation is always going to be part of this. There's a couple of places where you can't get away from it. So the first one that comes to mind would be UE emulation for, traffic loading tests to see capacity testing for your network. It's not really feasible to bring hundreds of smartphones into a lab and to try to load your network. So use an UE emulator for that, for example, to simulate traffic from 1,000 subscribers on a site. The other one that comes to mind would be modeling the link impairment for mid-haul, front-haul, backhaul connections, modeling packet loss or bandwidth changes, or latency or jitter, or things like that to see how the network reacts. So those are examples of where you want to emulate some real-world behavior, still even within a mirror lab. I think the key there is to try to integrate those into the orchestration system to the maximum extent possible. I know we do a lot of that with, when a customer says, can you bring this piece of equipment into the system? And as long as it's got an API, we say, yes, sure, we can do that. So I think to make the most use of those the emulation equipment, you'd want to, integrate them into the orchestration system.
Okay, great. Thanks, David. Second question. Before we get to that, actually, just there was a bit of a hiccup, I think, with some of the names. If you find that your name was improperly represented when you came into the webinar, please do send us a chat and let us know what your name is, because I do want to send attendees to this webinar or something specific. So please do provide your name, and we'll get that to you. So second question here, David, is building another network in the lab is expensive and takes more space than regular test equipment. How much benefit is there really?
I have a number of answers to that question. So let's think now for the cost of not doing it, right? So there are things that you can't test otherwise. There's some of the more sophisticated testing scenarios that you simply can't do any other way. And there's a recent example of a fairly major operator that made a change in their production network, and it took their network down for many, many hours, basically an entire day. They had no service. And I'm sure that change that was made was tested on the hardware, but I doubt that it was tested in a network environment to see how it would perform and how it would interact with other parts of the network. So the risk of not having sort of a captive replicated network in a captive lab scenario to do this kinds of testing can result in you deploying things into the field that might be very expensive. So there's the opportunity cost of not doing it. The other way I'll answer that is an orchestration system like Lambda will allow you to minimize the investments you need to make to create this mirror lab, because everything is shared. So you don't need to replicate all the equipment for every tester. And every engineer does not need to have a base station on their desk. There's a set of base stations that can be in a lab somewhere. and they can be shared by everybody. So it allows you to sort of optimize the investment you make in the space and the capital assets to do it. So yeah, obviously testing costs money, but there's a very, very strong rationale for doing it. And an orchestration system approach like this will help minimize some of those costs.
Okay, thanks, David. I do have one final question here. Again, if anyone has any specific questions, please use the Q&A button icon at the bottom there. Final question I have here, David, is you showed multiple switch matrices feeding into the same shielded boxes in one of your diagrams. Why can't you just use a large switch matrix?
Techie question, like that. So within reason, you can. In certain cases, you can just make the switch bigger and feed more RUs into a bigger switch. They tend to come in different sizes, usually 8 input ports and then 16 and 32, and they can go as high as 64 and 128 input ports. And if you've got a big lab, you could have hundreds of RUs that you want to plug into those. The bigger the switch, the higher the insertion loss, and that can affect your link budget calculation. So you may not end up with enough signal dynamic range at the device under test to perform the testing that you need. So one of the ways around that is to use larger numbers of smaller switches operating in parallel. And your orchestration system can treat them as one larger virtual switch, but they're physically smaller pieces of hardware, so their insertion loss is manageable. And then you do the final combining inside the chamber. But that's a good catch. So there's also other ways you can approach minimizing the number of ports you need on the switch as well. So there's some RF combining approaches where you take 100 RIUs with 4x4 MIMO. You can combine the MIMO ports together. You can combine them by site sector. So there's a number of different ways you can do to minimize the number of ports you need on the switch to try to keep those costs down as well. So.
Okay, David, I think those are all the questions today. I think a reminder to the audience there, if you want to reach out, feel free to reach us out. Oh yes, thank you, David. His contact is there. Any questions related to any of the architecture diagrams or any of the technicalities, like far, just give them a call even, or send them an email.
Yeah.
Also, there will be recording of this webinar if you came in late. And we'll post this afterwards, all the attendees and registrants aware of the recording, so that you weren't able to join for the full session. You certainly can do so at that time. And I guess the final note is that this is just one of many further webinars we plan to do in our series. There are other ones that we did do earlier in the year as well, and we'll provide those resources. And we also have a white paper as well, where we took an actual customer use case for those that are interested, and we'll provide those sources. So with that, I think that concludes everything. David, did you want to mention anything further before we conclude?
That's it.
Here?
Just again, thank you for your time and attention today. And like David said, this is my contact information. If there's anything in here you want to, you're too shy to ask in public, feel free to reach out to me directly, and we'll be happy to talk through it.
Thanks everyone for joining, taking time out of your day, and hopefully see you soon. Take care.
Bye all.